All right. Okay, so guys, welcome back. Today we're going to wrap up chapter 6. We'll see how that goes. And then on Thursday is the second exam. So anything we get through today may appear on it from not chapter 6, sorry, chapter 11, SN2 reactions. Okay, so anything if we get to SN1, E2, or anything other than SN2, it won't be covered. It won't be tested. Okay. So I'll make a note what won't be tested, so you know like what not to ignore. All right, so just a few announcements here. Exam 1 corrections are due tomorrow. I'm sorry, not tomorrow, Thursday. And then the first round of extra credit assignments are due on exam day. So office hours, campus wire, tutoring, study groups. And I believe that's it. If I'm missing one, let me know. So tutoring, study groups, office hours, campus wire, exam 1 corrections. So if you want a little extra credit, boost your grade, those are due by Thursday, okay? And if it's after Thursday, like say, you forgot Friday morning, that's okay. But like you're busy on Thursday after exam, but after Friday, I won't accept it. Okay, so you'll lose your chance of getting extra credit by then. So I'm kind of be more flexible, but still be firm on here so that no one's submitting extra credit like on the last day of class. So we don't want that situation. Okay. All right. So remember study groups. If you study with some people in class, that counts. Tutoring. If you go to my office hours, attend Marisol's office hours, that can be considered tutoring. So you record your sessions there. And then for SI will still just be limited to the quiz replacements. Okay, so those SI sessions are structured. They're not like Q&A type things. So we'll keep that separate. All right. And then if you go to outside tutoring, online tutoring, it has to be with someone, no AI. So you can't just Google search everything, okay? If you meet with me, if you come talk to me and work on some stuff for at least 40 minutes, that can count as one tutoring instance or session, okay? And then campus bar, if you're actively participating, I will know. I will see how much karma everyone has built up, okay? So basically every 10 points, rounded down, will get you 1 point extra credit, okay? For example, if you have 9, that doesn't count. So 39, it does not count as 4. That counts as 3, okay? So I mean it when I say rounded down, okay? Because in campus bar, it's a little bit different. It's going to like self-study on there. And so that's the policy on that. Okay. Are there any general questions before we start? Continue here. Nope. So I handed back all the quizzes. If you didn't get your quiz, please come see me. I think that'll be useful to study. Okay. And like I said before, this exam will focus on cycloalkanes, stereochemistry, and the SN2 reaction that we've been going over for the past week. Okay. All right. So last time we were talking about basicity. Okay. So let me just rewrite what we had before. Okay, so remember, leaving group ability is based on the strength of the base. Okay, so the stronger the base, the more reactive you are. So strongest. All right, let's see that strongest base. All right, let's hope this doesn't crash today. All right. So CH3. So first we were comparing negative charges, right? So CF3 is the CH3 is the strongest base, so not the most best leaving group, okay? But if we had to choose, the trend is this way. So OH, and then lastly, if we look at the trend in base strength, these are considered strongest to weakest base. So weakest base here, meaning most electronegative, doesn't want to act as a base because it doesn't want to share its electrons. Okay? So the order here, if we draw an arrow going this way, this is the order of increasing leaving group ability. All right? So this is the order increasing leaving ability. In all our examples, we never showed a carbon group leaving, and that's because it's the strongest base. It won't leave, okay? With radical halogenation, that was an exception because you formed a radical. So a radical can cleave any type of bond. So it's possible to cleave carbon-carbon bonds that way. But in this situation, if you have a lone pair forming on the carbon, that's not really good. So it's not going to be very stable. Okay, so this is the order of increasing leaving group, leaving ability of the leaving group. Okay, so the stronger the base, the more difficult it is to leave, because remember when we talked about acids, if the conjugate base is strong, the acid is going to be very weak. All right, so this is a poor leaving group. So it all comes back to acid-base chemistry a little bit. Okay. And then fluorine here is the weakest base, so that's the easiest to leave. So that's kind of correlated to the conjugate base of acid strengths. Okay. All right, so there's some other leaving groups we should be aware of. So the leaving groups that we talked about before, remember halogens are usually what you see as good leaving groups, okay? So we talked about that last time, but there's some other leaving groups that we see as well. So let's talk about those. So let's talk about some other leaving groups. So the leaving groups here, they are especially good, and that's because they're conjugate bases of very strong acids, but they also have another property. They have resonance, okay? So yeah, that term will never go away here. So if we're still having a problem with resonance, please review. All right, so they're all based on this sulfonate group. So SO. So there's a bunch here that we'll go over. All right. So if we ignore the methyl group there, what does this look like? What polyatomic ion you may have seen before? If we ignore the CH3, what does that look like? What's SO4 2 minus? What ion is that? Close. Is it sulfite or sulfate? Sulfate, right. So we could use this in organic chemistry, but we just changed some of the groups. We derivatize it. So this is called methyl. So here it's methyl because there's a methyl group right here. So methyl, this is called methyl sulfate. Okay, so this is a conjugate base. It's like a conjugate base of sulfuric acid. So very strong acid. This conjugate base is very weak, is a weak base. So it doesn't do anything but leave, okay? All right. Now we're going to talk about some other groups. So some of these names you may see again, okay? So we have methane. All right, sulfonate. All right, so same group as methyl sulfate, but instead of an extra oxygen, we have an R group. So when this R group is methyl, we just write methyl methane sulfonate, okay? So we don't call it sulfate anymore. It's a group attached to methane, which is 3, CH3, okay? And then sulfonate is the sulfur group, the SO3 ion. That's a sulfonate, okay? So this has a specific name. This is called mesylate. Or some people call it mesylate. Okay, and the abbreviation we commonly use is MSO minus. Okay? So if we kind of think about this charge here, look at the O minus. Where can we draw some resonance structures where the O minus is moving? So think about how some resonance structures you can draw where the O minus, the negative charge on oxygen, is going between the different oxygen atoms. So that's why these are good leaving groups. They're not only stabilized by electronegative atoms, they're stabilized by resonance structures as well. All right, so we're going to talk about 2 more here. So O minus, again. And then it's another sulfonate group. This is one of the most popular ones, okay? CF3. All right, so how would you name that CF3? All right, there's 1 carbon atom, right? So trifluoromethane. So let's go over there. So trifluoromethane. All right, let's put on the second line here, sulfonate. All right, so this is commonly called triflate. Triflate ion. So this is called the triflate ion. It commonly has, I think it's TS. No, that's Toslate, sorry. TF. I think it's TF. So we commonly abbreviate this as TF, OTF minus. All right, let's put that over there. TF, O minus. That's triflate, okay? So there's mesylate, triflate, and then there's one more we'll go over. This one has a benzene group. So let's slide over here a little bit. Okay. All right, one more. So these are all great leaving groups. Okay, these are even better than iodide. All right, so these are the best. All right, but sometimes these are hard to get rid of. So it has kind of like advantages and disadvantages. For our purposes, we won't care about like if it's green or sustainable or not. We'll just be considered like, oh, is it a good leaving group? If so, yes, then it can do a great SN2 reaction. Okay, so the last one here. We have an oxygen atom again, O minus. Okay. All right, I'm just going to draw the benzene ring here so you understand how it's bonded. All right, so this is has a benzene ring in here. So there's other derivatives too, like this one, but we're just going to focus on these 4, okay? And out of these 4, the latter 3 are the most commonly used, okay? So this is called 4-methyl benzene sulfonate ion. Okay, it's also called P here. So P stands for para. So look at the benzene right there. So it's substituted at opposite ends. That's called para. That's the para position. You don't need to understand what that means right now, but that's how we indicate that it's substituted directly across the ring, 1,4. Okay, so this is called para-toluene sulfonate ion. All right, so that's a mouthful, so we don't say that. We say tosylate, okay? So this will be tosylate. TSO. All right, so these are the groups here. So these could be leaving groups: tosylate, triflate, and then mesylate. So these are great leaving groups. Okay, so let's talk about the relative ability of these groups. So here's the leaving ability. Okay, so TSO minus is greater than mesylate, which is greater than, all right, mesylate, yeah, I don't know, all right. Well, I think that one's greater. All right, guys, let's move this one over. Sorry about that. So, triflate comes next. Greater than mesylate. All right, greater than methyl sulfate. And then the halogens fall into place. I minus, Br minus, Cl minus, like that. All right. So let's go over why some of these groups in particular up there, why are they so good at leaving? All right. So let's use triflate as an example. So let's draw the structure of triflate again. So triflate So notice here that there's great resin structures, but what's also special about the CF3 group? Would you characterize that as a withdrawing group or a donating group? With those 3 fluorines right there. Let's just draw that structure out as well. So let's draw this out as 3 fluorine atoms. All right, so what do you think the fluorines are going to do? Yeah, it's going to take those electrons. So it's going to take the electrons. The electrons are actually going to flow this way. So that's my dipole moment. All right, so the electrons are flowing this way. So electron density are going this way, okay? We have a partially positive carbon here, partially negative fluorines, and this is going to further impact the direction of this O minus, where it has a negative charge here. So electrons are going to flow to that carbon because it's very electron deficient, okay? And then we can also draw resonance structures, so that actually places the negative charge directly on the other oxygen atoms, okay? So we can draw one here. Then we get this structure. And then we could draw another one, right? Where else could we put the negative charge? All right, not on the left oxygen. We already did that one. Which oxygen? The south one, yeah. So then we could just take this guy and move these electrons here, right here. So the charge now is very stabilized because it's being shared or being delocalized across different atoms. Okay, and the closer it is to the CF3 group, the better. So that's more stable. Oh, my bad. Nope. Back. All right. So here, leaving group of ability here is enhanced by resonance. Okay. So we can draw resonance structures. Now, tosylate, you can have many resonance structures, but we won't draw all of those today. But you can imagine tosylate is even greater because the benzene ring could also help delocalize some of those electrons. And you can form additional resonance structures. So you can actually form more than these three we drew right here for triflate. All right, so that's the leaving group. Are there any questions about the leaving group? So leaving group, so these are all conjugate bases of weak acids. So these are conjugate bases of sulfonic acid, okay? So all these here, let's put this in parentheses. Conjugate base of sulfuric and sulfonic acids. So imagine if we put an H onto the negative charge, that would be called a sulfonic acid. So these are the conjugate base. And these are very strong acids. So that's why they're considered great leaving groups. Okay? So if there's any way we can stabilize the charge as it leaves, that's going to be a very good leaving group. So tosylate. So anything that's negatively charged, it has to be a conjugate base of a very strong acid. Okay? And then in the future, we'll see what happens when the charge is neutralized as it leaves. That's another criteria for a leaving group, but we're not going to talk about that yet. Okay? So we should know like which ones are good leaving groups, bad leaving groups. We kind of talked about that last time. Okay? So just think about, is the base or the leaving group, is it the conjugate base of a strong acid? If it is, it's a good leaving group. So, for example, HF, not a strong acid, so F is bad compared to this list we just wrote out. Hydroxide, that's a conjugate base of water, not a very strong acid, so that's also a horrible leaving group. Okay, so hydroxide and fluoride, those are the two common leaving groups you might expect to leave, but they're pretty bad. Okay, so I would just jot down hydroxide, OH minus, F minus, worst leaving groups you will encounter. Okay? All right, so we're going to move on now and talk about the nucleophile. Is there any more questions on the leaving group? No? All right. All right. SN2 reactivity, the nucleophile. All right. So basicity and nucleophilicity, they may sound like the same thing, but they're actually a little bit different. All right. So nucleophilicity. So let's just go over that term. All right. So it's measure of how easy, I guess, or how easy / readily. I mean, it's ready to attack, okay? So how readily a compound or an anion is able to attack an electron deficient atom. All right. In our case, in our discussion of SN2 reaction, okay, so for an SN2 reaction, so let's just write that here, SN2 reaction, what this means is how readily a nucleophile attacks an sp3 carbon atom, all right, bonded to a leaving group. So this special criteria, this won't work for a linear carbon, and it won't work for a planar carbon, only tetrahedral, okay? So the geometry plays a big role here, just like we've been talking about the shape, the orientation, the conformation, plays an important role in stability, and in our case is now reactivity. All right, so let's go over a few concepts here of what makes a good nucleophile and a bad nucleophile, okay? All right. So there's a few factors we have to consider. So here we're going to consider a nucleophile depends on, all right. So your nucleophile strength, or how good or bad it is, depends on a few things. Depends on one, charge. All right. How basic it is, basicity. Okay. Solvent. Polarizability. This is the size of electron cloud. Okay. And, oops, sorry, let's erase that. The last thing here, the nature of the substituents. So based on the identity of the substituents on the nucleophile, is there something nearby will affect the nucleophilicity. All right. So let's go over down the list here. So base it on charge, all right? So charge, let's go over charge first. So let's do number one, charge. All right. So you're more reactive when you have a permanent charge there. Permanent negative charge, that's going to react faster than, say, something that's only partially charged. Okay, so let's observe two examples. CH3, Cl plus hydroxide. Okay, to get methanol plus Cl minus. So that's SN2, right? So this is very fast. All right, so let's use that example. Now let's compare the very similar reaction where we use water instead of hydroxide. Okay, so CH3 Cl plus H2O. All right, so we have the same products here. CH3 OH plus HCl. So we have the same products, it's just the leaving group now is protonated, okay? So this is very slow, very slow. In fact, I don't think a reaction even happens. So very slow. So the nature of the charge tells you how reactive it is, okay? So let's just use a similar example now. Let's use nitrogen, okay? So let's go back this side really quickly. All right. So notice here, this is very fast, even faster than hydroxide. Does anyone have an idea why? Stronger base, good. So stronger base, and that's because it's less electronegative, right? Likes to share its electrons more, so better base. Very good. All right, so take that example. So nitrogen, better base, so better nucleophile, faster reaction. And we see a very similar thing if we use ammonia compared to water. Okay, so water is very slow, but if we do the same reaction in the presence of ammonia instead, you'll get a reaction, but it's slower. So not as fast, but it still can be done. Okay, so you get CH3. NH3, Cl. All right, so now here, this has a positive charge, the nitrogen, and the negative charge is on chlorine. So now you form a salt. You form an ionic compound. Okay, so depending on what form of it you use, you're going to see different products, but they're pretty much the same thing. They're just in a different kind of form. All right. So that was charge. So charge here, if you have charged nucleophile, they are better than uncharged ones. All right, so that's charge. Are there any questions on the charge ones? Okay, so now let's go over basicity. So let's use basicity now. So here we have, sorry, I spelled it wrong. All right. So in this case, if you same nucleophilic atom, okay, more basic atom is more nucleophilic. All right, so let's compare. So let's draw a few structures here. All right. So again, it's good to consider the pKa, or the base strength, okay? So let's do pKa of our conjugate acid here. All right. So acetic acid here, the pKa, if we had acetic acid, so acetic acid would be the pKa. That's talking about acetic acid where the hydrogen is attached to the O. So that's a pKa of about 5. Okay. Now let's take this next derivative, and this is called phenol. This one. So this pKa is about double, 10. Both of them have resonance structures, but it's better to put a negative charge on an adjacent oxygen, not a carbon. So that's why this one is a relatively stronger base. All right, the resonance structures are not very stabilizing in this case. Now, in this example, we got rid of the benzene, and now it looks like phenol, except now there's no chance to do what? in this case. Yeah, there's no chance to resonance. So this is why this is so unstable, the most basic. So pKa equals 17. So if you're thinking about pKa's, the conjugate base of that acid is the strongest base when the pKa is the highest. Okay, so that's why the one on the right is a way better nucleophile than acetate. Well, sorry, that's not acetate. Benzoate, right there. It looks like acetic acid. Sorry, it's not acetic acid. It's the benzene variant of acetic acid. Okay, so here's the order. All right, so order of increasing basicity and denucleophilicity. Okay, so the ones on the right, as you move to the right, it makes a better nucleophile. Like that. All right, so we can make some generalizations in the periodic table. But if you have the same atom acting as the nucleophile, that's the one forming the new bond, that's going to be dictated by the strength of the substance as it acts as a base. Okay? So the stronger the acid, the weaker the conjugate base, the weaker the nucleophile. And the stronger the conjugate base, the stronger the nucleophile. All right. Okay, so the next, we won't talk about solvent yet. So let's talk about on the periodic table. So we can make some trends on the periodic table. So across a row on the periodic table, as electronegativity increases, okay, what can we say about the nucleophilicity? So tell me about the ability to act as a nucleophile. If I'm more electronegative, am I going to act more as a base? No, I'm going to hog the electrons. So nucleophilicity should go down or decrease, all right? So the nucleophilicity just think this as a property of being a nucleophile in a reaction. Okay? All right, so let's make some generalizations here. Weakest base F minus, OH minus, NH2 minus, and then CH3 minus here. Okay, so here it's the opposite, right? Remember we talked about leaving group? Now it's the opposite. Strongest base and here we have increasing order of nucleophilicity. In other words, nucleophilic strength. All right, so if I gave you a list of nucleophiles, you should be able to pick out the one that's the best, and you should base it on electronegativity. The lowest electronegativity, the strongest nucleophile. Okay, are there any questions about that trend? So we talked about charge. All right, nucleophiles are better when they have what charge? Negative, right? Better than neutral. And anything that's positively charged that can act as a nucleophile, it doesn't have electrons anymore. That can donate. Okay. All right. So let's go to the picture. All right. Now we're going to talk about solvents. Okay, so let's draw a line under. Well, we'll just highlight this. So now we're going to talk about solvent. Okay. Okay, so solvents have two classifications. Does anyone know those two? So your solvent is either what or what? Close. Not quite. That's a good guess, actually. You're right. You can classify it as them. But usually we classify it as solvents, they can either dissolve polar substances. What's the other side of that coin? Non-polar, right. So your solvents have two categories, okay? So your solvents have two categories here. All right, non-polar and polar. All right, let's talk about some non-polar solvents. So non-polar solvents are basically hydrocarbons, all right? So any hydrocarbon solvent. So hydrocarbons or halogens or haloalkanes that are nonpolar. So they're nonpolar by virtue of their symmetry. So for example, we can have pentane, C5H12, hexane, C6H14, or something like CCl4. So those are common nonpolar solvents, okay? So they're basically just hydrocarbons, or you have a tetrahedral arrangement of the same bond, so like CCl4, okay? So those hydrocarbons, very nonpolar. And then then you get into the range of solvents that have slightly polar, polar, and very polar. They all fall under the term polar solvents, okay? And then polar solvents, you have two classes. One that acts more like hydrogen bonding, and one that doesn't. So those have two names, so protic versus aprotic. So A just means it's the opposite of the word that comes after it. So aprotic basically means any polar solvent that does not have any OH or NH bonds, okay? So protic, some common examples. All right, what's the solvent we know that has OH bonds? It's the most common solvent in the world. We drink it. Water, H2O. We can't live without it. H2O, right? All right, under here you have alcohols, ROH. Those are alcohols, like ethanol. And then you have amines and carboxylic acids. So amines here, RNH2. And then the other one here is carboxylic acids, RCOOH. So those are protic solvents. So those are your most common protic solvents. Alcohols, water. If your reaction can tolerate it, amines. Okay, then we have aprotic. All right. So aprotic solvents, these lack OH and NH bonds. All right, and I'll go over some of these in a little bit, okay? So for our reactions, if you have charged species, non-polar solvents won't work. It won't dissolve anything. So that's why we're focusing for this chapter on this side, polar. We're going to look at polar solvents in this section, all right? When we deal with non-polar reagents, we'll talk about non-polar solvents, okay? All right, are there any questions about the solvent selection? here. So not yet, but there will come a time where you'll have to remember some of these solvents, and as part of the problem, you'll have to say, okay, what reagent do you put, and then also what appropriate solvent do you put. You're not going to write any solvent because that wouldn't work, okay? So you'll have to remember some of these solvents, okay? And always write the ones you should remember. Okay, so let's go over why the solvent's important, okay? All right. So why is solvent important? So the solvent does something called solvation, okay? So I'm going to make a point here. Protic solvents interact strongly with your nucleophile. Okay, so what happens here is the solvent will form a tight solvent shell around your nucleophile, and that will prevent it from reacting. Okay, so they interact strongly with your nucleophile, can inhibit or trap the nucleophile. Okay, so for example, look at your nucleophile here. Okay, so for example, if you have an alcohol, okay, so the alcohol can encapsulate it and trap it. So these are, so your nucleophile here is negatively charged, right? Or delta negative, right? Your hydrogens here are all delta positive, so those will form very strong hydrogen bonding interactions, okay? And it can circle around your nucleophile and trap it in there and prevent it from being able to reach your electrophile or your alkyl halide. All right, so there's a lot of these interactions here that prevent it from reaching your destination, okay? So these things matter in terms of reactivity. Okay, so here your nucleophile will be trapped, okay? All right, so this is a big issue for small ions like F minus, O minus, and N minus, comma, C minus, okay? So that's a very big issue for your most basic nucleophiles. So they have a smaller atomic radii, and they're so small that the solvent will just completely bury them like a micelle, like a soap bubble. Okay, they trap them. Now, this is not an issue for bigger ions, okay? So here, rate for SN2 reaction is greatly reduced. All right, so it can't do the reaction. So that's why in a typical SN2 reaction, the best thing you should do is use a polar aprotic solvent. No hydrogen bonding, okay? All right. So this trend here is completely reversed for large nucleophiles. So say this is my small nucleophile. I'll draw a circle around it, okay? Very small. Now let's imagine we have a big nucleophile like iodine, okay? So this is not an issue as an issue here, okay? All right. All right, so not an issue for, so here, not a problem for large / polarizable ions, like iodide. Okay? So remember, polarizable means you have a squishy electron cloud. So you have regions where, you know, so say these are all the electrons for iodine right here. So the negative charge is really mostly over here, and the positive charge is mostly over here. So when you have that situation, the solvent molecules won't distribute all around your atom. They'll only be on one side, because of this distribution of charge in the electron cloud right there. Okay? So polarizable means you can have separation of charges here. So this side, and that's because the large atom here, the charge is more distributed and it can easily redistribute. So these solvent molecules are not an issue for larger ions. So that's why iodide is more nucleophilic than fluoride in this situation. Okay? All right. So there's a trend here. The strength of your nucleophile depends on what solvent you're in. Okay? So let's go over that. All right. So let's talk about nucleophilicity. All right. Of halides in protic solvents. Well, we know that the smaller the halogen, the more inhibited it will be. All right, so fluorine here is dead last. Okay, and then what comes before fluorine? So what's the next one? No, so just think of the halogens. So bromide, then chloride. So which one's the largest? The halogens. Iodide, right? Good. All right, so iodide's inhibited the least. So its charge is available to do an SN2 reaction. But fluorine is not, because it's tied up by the solvent. Okay? So you won't see this tight arrangement in apolar solvents. Aprotic solvents. They're still polar, but they're not as polar as these protic solvents, so they won't interact as closely. Okay? So in protic solvents, that's the change here. Okay? And then in case of aprotic solvents, it'll be different. Okay? But that's what I want to talk about. Okay. So here we could write arrow here, okay? All right. Increasing nucleophilicity. So, increasing nucleophilicity. All right. And then on here we have this arrow, increasing solvation. All right. So what do you think the trend is if we switched from a protic solvent to aprotic? What do you think the trend is now? The opposite, I heard it. It's the opposite. So you're not inhibited by hydrogen bonding. The opposite trend will be true, okay? So now fluoride is the strongest in aprotic, okay? So I would say here's the trend in aprotic solvents. Okay? All right. So the trend is reversed. All right. So now let's talk about, before we take a little break here, let's talk about, all right. You said we have to memorize some solvents. So what are they? So we're going to talk about them, okay? So now let's talk about some common polar aprotic solvents. All right? So here we're going to write some valuable polar aprotic solvents. So let's underneath that. Okay. All right. All right, let's go down the list. Acetonitrile. All right, acetonitrile is CH3, H3C, CN. There's a triple bond there. Okay, so that's acetonitrile. The nitrogen is polar. It's going to pull electrons towards itself. So this is a polar solvent. All right. All right, we have dimethyl sulfoxide. So this guy looks like this. SO CH3 CH3. All right. You might have methyl sulfoxide, and as long as it's right on your skin and you touch it, you may get the smell of garlic. And that's because sulfur is one of the prime atoms in garlic. Okay? So weird fact. But all right. So now let's talk about another one, DMF. So this is another common one. So we abbreviate this as DMSO. All right, now we have DMF. So this is called dimethyl formamide. Let me see if I spelled it right. I don't know, form. Yeah, it's form, then amide. So this has abbreviation as DMF. This abbreviation for acetonitrile, we write it like this, methyl CN. So that's acetonitrile. So if you ever see that on, like a homework problem, that will be the abbreviation. All right, acetone. There's no abbreviation for acetone. But this is the prime component in some beauty products and a very common organic solvent like we saw in the lab a few weeks ago. So that's acetone, so a common solvent, okay? And then there's a few others here, so let's just scroll down a little bit. All right, we have CH3NO2. So remember, NO2, right? What kind of group is that? Withdrawing or donating? Withdrawing, right? Lots of electronegative atoms there. So that's a very polar solvent. Okay, so this is nitromethane. Okay, so that's another one. And then this one, all right, this one has a long name. Hexamethyl. This solvent is no longer used anymore because it's a carcinogen. All right, so hexamethyl, phosphoric, all right, hexamethyl phosphoric triamide. All right, what does this look like? So this has abbreviation, but it looks like this. So P double bond O. And you just look at it, it kind of looks like a nerve agent. So no wonder it's been banned, or no one ever uses it anymore because of its scary looking structure. All right. All right, so this is called HMPA. All right. So, of the common ones you'll see in the homework, I will highlight them. This one, this one, this one. So all of them really, except, well, not, you rarely see this one. So the ones, the top row, those are the most common polar aprotic solvents. And the last two, some of them are just used as necessity. Nitromethane is sometimes used. HMPA, I've never touched that chemical, so no, we rarely use that. Okay, so when we get back, we'll now talk about the substrate's influence on SN2 reaction. Okay, so the substrate also matters. All right, so let's take a little break here. I'm going to refresh the page because it might slow down, okay? Hello?
Yeah, but I was like, why did you sit so closer?
Hello, what's up?
She asked me to tell you that she was going to send you an email later.
Who?
Evelyn?
Evelyn? All right.
Yeah.
Yeah, I don't see her.
Yeah, she said she's going to email you after.
Okay, got it. Emily here? No. Kim? Kim here? Kim? Isaac. Thank you. Maria. Okay. Isaac. Is Kim here?
Yeah, because I can wear more. I'm not gonna dress that today. I just did it today. I was planning to, but we had like
Oh, what's up?
Hypothetically, for if you have like the small ions in a, I'm trying to remember, with the protic solution solvent, if you have more of the ions and you have the protic solvent, is that still an issue? Where the solvent is still surrounding?
No, but usually, then you might have issue with solubility, getting everything in solution. Yeah, so that's the interesting point. I wonder if you make it like more concentrated, will that maybe help speed it up? But then I think you might run into issues where everything doesn't dissolve as well. But that's one way you can counter it. Yes, you could make it more concentrated, right? No, I mean, it's just a solvent, right? It just helps bring everything in solution. It doesn't react. Yeah, because you can't just say throw this in there. Nothing will happen. Everything has to be in solution, or like in solution as liquid, dissolved in liquids, or in the gas phase. But we rarely talk about the gas phase in chemistry, so that's why everything's in solution.
So even as it says, like, it'll be most likely to be increasing the speed to like at least 2
Right. Mm-hmm.
Oh yeah, I always drop it. Yeah.
And then if it's like a wedge, it's always gonna be opposite.
Yeah, so if it's like, if it's wedge, yeah, 'cause it's like, if it's like coming at you, then it's like, you're like B and C here, that's like A, B, C goes to the right. The A is back here, then goes A, B, C.
If it's like going, it's like
I like always do it with my hand, like coming at me, B and C, then like there, it's going backwards, and it's like, oh.
So the thing is that if you don't have insurance, if you register as a student, like you have to fill out a form that says like I have my own insurance, here's my insurance and what's the benefits. And then they're like, okay, you don't need shit, so then you can do it. But if you don't fill that out from a certain time frame, they automatically assume that you need it, so it's like $2,000. Should they be filling out? But then I was like, but there's an option for like a late fee waiver. And it's like, okay, we have a lot to pay first to fill it out, and you have to pay like $50 fee. It's like, I'd rather pay $50 for that. Yeah. And so I'm like, I did that.
Yes.
I did it September 21st. It's like, I was on registered for class until like October 20. So I was like, I didn't fill it out, the form during the regular time. So I wasn't sure if I was going to do it in the fall. And so I ended up like waiver, but then like it didn't.
Remember, if this one leaves, it becomes a minus.
And then
Right.
I'm not yesterday.
This one leaves and becomes H2O. And water is the weaker base than hydroxide, so that's why that.
Being like, oh, here's how you do it. Here's your name with that picture. And it's like, here, please confirm your enrollment. Here's your assessment. You're not on that.
Huh?
It's like 3 or 4 years
Yes.
less off that was not approved during the legal year. Is this the official? My form is not. Right. For any notification, so I like called.
Mm-hmm. Yeah. Okay. Well, no. Remember, this is your alkyl halide. That's your nucleophile, isn't it?
Went to California, and he was so over it, but I could solve it all myself. Like, this is a fraternity house. I'm not surprised.
Because that's the nucleophile. And remember,
No, I mean,
your product should be neutral. So if you want to sign on, you might have to
Secrets inside.
Oh, yeah.
Because there are like all these.
No, so what happens here? So this is the nucleophile, right? Or something like that.
There's no way to open it from the outside that anyone else knows.
The nucleophile. So this is don't yeah.
And you.
CH3, yeah.
But like, there's always like one right next to this girl, like right in there.
It has to be neutral. That's why hydrogen finished. So when you form this bond, it becomes an ammonium ion, NaH. It'll be NH2CH3 plus. It is the fraternity. So this is how you chemistry you have to work it
But
up.
it's like honestly
So
just.
you get an ion, we can isolate that, so you just work it up and try to.
Yeah.
No, it doesn't have to. So some atoms are nucleophilic, just by virtue of the atom itself. All right, guys, let's continue on here. We're almost done with the first half of this chapter, which is like almost all SN2. Okay. So, lastly, we have to talk about the substrate. So you notice here that most of the reactions that I picked, they were all pretty much methyl or primary alkyl halides. There were rarely any secondary ones, and God's no tertiary ones. And there's a reason why for that. Okay, it has to do with what we talked about previously. All right. So the last thing we'll talk about for this chapter, and this will be the end of the material I will test. Okay. So SN2 reactivity. And the substrate. So this is the nature of the substrate, okay? All right, so let's say we have our generic reaction here. R, bromine, okay, plus iodide. And it gives us Ri. Here, mine. Okay. So, what is R? So, if R is methyl, all right, so let's write our situation. So, if R equals CH3, okay, if R is CH3, if it's CH3, CH2, if it's isopropyl, all right, or if it's tertiary, CCH3, CH3, CH3. So we have a methyl primary alkyl halide, secondary alkyl halide, and a tertiary. So look at these carbons here. So this carbon, primary, this carbon, secondary. This is where it attaches. And this carbon, tertiary. Okay? So at each of those arrows, that's where it's attaching when it's in our group. Okay? So the bromine will be directly attached to the carbon atoms I'm pointing to. Okay? So now let's talk about the relative rates of reaction. So relative rate of reaction. So relative rate here. So it's methyl is 145 times faster than the one that is the base number. And the base number one is our primary. So this is only as fast. Okay, so methyl is 140 times faster than the ethyl group here. Okay, now compared from the primary to the secondary, that's slow, but not totally bad, but it's not good. Okay, so not the best. All right, it's like 1/1000th as fast. And then for the tertiary, there's no contest. There's no reaction. So this is called negligible. Which basically means no reaction. All right, so if you can't measure any product, get a mass for the product you made, no reaction. Okay? So, but why would this be the case? So let's talk about the transition state again. All right, so remember here, iodide is our incoming nucleophile. And bromine here is our leaving group. Okay? All right, so remember when we drew them all H's? The iodide could approach. But as I start to substitute here, so if I get a methyl group here, all right. So what do you think is going to happen if I have more carbon groups around the central atom? And remember, these all can rotate. So these can all experience repulsive forces. Okay, so the iodine here is going to experience steric hindrance. All right. So too much steric hindrance as carbon is more branched. So this becomes a problem in the transition state. Okay, so this then here, this energy of the transition state here becomes too high. All right, so this is a problem so this is an issue, for example, for secondary and tertiary substrates. So primary is not a problem because the carbon group can just rotate out of the way. All right, it can rotate out of the way, and so it only sees that a dearth of a time. But for tertiary, there's no way to get rid of that because every time you rotate, a methyl group is going to interfere And so no matter where the iodide tries to approach, the only way it could probably approach is the front side, but we know that's not how it works, right? So that's why that's why the rates are this way. And it has to do with steric hindrance. So the things we've been talking about leading up to this, this moment for now, okay? So SN2 does not work for tertiary substrates. So that's why there's no reaction here. And it has to do with steric hindrance, okay? So it doesn't matter what the so like your nucleophile, if your nucleophile has a carbon group, that makes it even worse because the carbon groups have to approach each other for both your nucleophile and your substrate, and that also can be problematic, okay? So this is just one of the issues organic chemists have to deal with, okay? It's just something we can't do, which makes it both, frustrating, but also a challenge to overcome, okay? All right, so that's branching at the center of reactivity. Now, branching also matters at the site close to the reactivity. So there's another aspect we have to consider, okay? So this is the first one, slowest. So here we could say slowest here. Fastest. So when everything's hydrogen methyl, the best reaction for SN2. When it's substituted at the center, so tertiary, not good. Okay, are there any questions on this picture? Sorry, I could have drawn it a little better, but if you built this molecule and you saw at the center there, you'll see that there's not much room for the iodide to kind of fit through and reach the carbon. The space is limited, so that's steric hindrance, okay? All right. Okay, so last thing we'll go over here for this one is if we have branched alkanes at the center of reactivity, okay? So now let's go here, and then we're going to talk about the relative rates of branched bromoalkanes with iodide. Okay. So again, we're going to do the same reaction. R, Br plus I minus goes towards R iodide plus Br minus. So we're doing an SN2 reaction. Okay? All right. So now let's take a different method here. So now let's imagine we have this group here. All right. All right. So here are different alkyl halides, and you notice here they are increasingly more branched at the second carbon, one carbon next to the site of substitution where the bond is replaced. Okay? So which one of these you think is the slowest? If you had to make a bet on it. Which one do you think will proceed the slowest in SN2? The most branched or the least branched? The most branched. So this is neopentyl. But look at here. What's this carbon? What kind of carbon is this still? What kind of carbon is that? Primary, secondary, tertiary? Primary. It's primary even though it's the slowest. So it does matter at substitution right next door to the site where you're reacting. So one carbon over, that will make a difference if it's branched or not. So this is still, they're all primary. See, all of them are primary. But the more branching you have here, the rate will be slowed. So very sluggish. So this rate is 1 times 10 to the negative fifth. So very slow. Not as slow as the tertiary one, but almost on the same level. Okay? So this is isobutyl. All right, isobutyl, 0.03. All right, this is propyl. .08. So not that different in how fast it is. And then ethyl here, that's our relative one. So this is 1. All right, so ethyl is almost, what is that? 100 times more faster than neopentyl. Okay, so branching at this position here. So branching right here will make a difference in your rate, okay? And if we draw another structure here, okay? So let's draw neopentyl. All right, so you have the bromine group here becoming more partially negative. Here's my carbon. My iodide is approaching. Now, okay, so there's an H. There's an H here, so let's do this way. And an H there. But there is a carbon group here, okay? And it's attached to 3 methyl groups. Okay, so the methyl groups can still get in close proximity, and all these other methyl groups, even though I drew them in the plane, they block the other areas on this tetrahedral carbon where the iodide could potentially approach. So it's blocked from the front, it's blocked from the rear, and then it's blocked if you try to circle back onto the side. So it's completely blocked by this branching carbon on the second carbon there. Okay, so you're still going to experience severe steric hindrance. So here, oh wait, sorry, I should erase. Sorry, this is partial charge, not negative charge. Quick fix right there. So still experience steric hindrance. So if you were to write a reaction here, this is going to be no reaction for sure. Okay? The other ones, they probably will react to some degree, but it's going to be very slow. Okay? So those are the rates for SN2. All right, so that's up to the part where we'll leave for the exam. So if I ask, okay, best substrate for SN2, pick the unbranched one. Okay? Primary, unbranched, methyl, even better. Okay? Then solvent should be polar, aprotic, and best nucleophile is the one that's the weakest base. Sorry, not the weakest base, but the conjugate base of the strongest acid. Okay? And then the least electronegative atom, if you had to guess. All right? And if you start on the homework, I asked all sorts of those questions in the homework. So if you get started in the homework, if you start already, kudos, you'll be in good shape. Okay? All right, so that's it for the first half. We'll spend 10 minutes talking about some new stuff, and we'll do that again before the exam, okay, just so we make sure we cover everything. I want you guys prepared for second semester, okay? All right, so this is a hard stop where we're going to say, okay, this is what we study up until the second exam. Are there any questions? No? Okay. So attempt my practice exam, do the homework. Those should be more than enough problems to help you work through these concepts, okay? But now let's switch gears here. All right. So now we're going to talk about a new mechanism. So volysis. Haloalkanes. All right. So say we have this reaction, RBR. So R is just any alkyl group plus methanol. Okay, so as written, this reaction will only take place if the R group is branched. Okay, so it depends on what the carbon chain is. Okay, so let me talk about the relative reactivity. In relative reactivity, I also mean the relative rates. Okay, rate of reaction. All right. So if I have just a methyl bromide, so CH3Br, all right, here we have all H's. Less than 1. H3C. All right, we have BR. All right, this rate is the baseline here, okay? Now if I have H3C, CH3, so a secondary carbon, the rate, okay, let's see, 1.2. Oh no, let's see, it's a 10. All right, well, I have to double check this number, but I think it's 10 to the second. All right, so we'll circle back here. I have to double check this number, okay? So question mark, 10 to the second, but it's higher than primary, okay? And then the last one, we get 3 CH3 groups here. (1.2) times 10 to the 6th. All right, so now it looks like our reactivity has somehow done what? From our previous example on the last section. Is it the same trend we saw, or is it kind of flipped? It completely flipped. So this kind of tells you that this mechanism is not SN2. It's different. It's still a substitution, but it's something completely different, okay? So here we can say mechanism is not SN2. All right, so it's something different. So the way we determined it was a different mechanism, we use kinetics. All right, so recall from 1B kinetics, you studied a reaction and you varied the temperature, you varied the concentration, and you recorded the time it took to make that reaction go to completion. That's what we do here. All right, so let's do a couple experiments here. All right, so here's some experimental data. So experimental data for kinetics. All right, so let's say we have our alkyl halide, and we add methanol. Okay? And here are the products. So tert, butanol, opposed to HBr. All right? So this is rate 1. So we calculate a rate. So let's just say it's rate 1, okay? We have 1 mole per liter. 1 mole per liter. Okay? So that's rate 1. Now, in order to determine what mechanism it is, you have to do kinetic experiments, and this is what we do. Okay? So then we did this same experiment almost, except now we're going to vary the concentration of one of the reactants. Okay? So CH3, OH. So we almost get the same product here. Well, we do get the same products. We're just studying the rate of reaction. All right? So here's rate 2. Okay. So here we determined, so when we double this concentration, now it's 2 moles per liter. And still we have to keep one of them constant first though. So we can see the effect of just doubling one. Okay? So it turns out that rate 2, just by experimental evidence, rate 2 equals 2 times rate 1. So it looks like this reaction is still dependent on the substrate, the alkyl halide, the electrophile, okay? But now let's see, remember when I said for SN2, if I doubled either the nucleophile or the electrophile, the rate increased. So it was dependent on both. And we see in the transition state, they both have to come together to react. But now let's see if that's true for this one. So let's do one more experiment. So this is experiment 1, experiment 2, now experiment 3. Okay? Now we're going to take the same reaction, but just do one more reaction here. And where we change the concentration of the nucleophile. Okay, so the product should be the same. All right, HBr. So this will be my rate 3. Okay, well, we're going to bring this bond back down to 1 molar, 1 mole per liter. And then methanol, we're going to increase the concentration to twice its value from before. Okay. Now, so we observed the rate, right? So now we'd observe rate 3 is very similar to rate 1. Approximately the same. So this tells us the reaction rate is only dependent on the electrophile. Therefore, the mechanism is different because it doesn't include both. Okay? And we'll talk about that next time. But here, let me just write the rate law. So rate is proportional to the rate constant K times your alkyl halide, RBr. Okay? So the rate here, we can now substitute, is equal to K times the concentration of CH3 CBr. Okay. And so then the K here, I think that we'll do like that. All right. So next time we'll continue talking about this mechanism, okay? And on Thursday, third lab, we'll take the second exam, okay? That'll be it.